Hello everyone. Today's lecture is on the inverse trigonometric functions. We will begin by reviewing what inverse functions are. In the inverse of a function, the range of the function becomes the domain of the inverse function. In other words, the y values, the output values from the original function becomes the x values or the input values into the inverse functions, and the domain values of the original function becomes the output values, the y values or the range of the inverse function. So with that in mind, we are going to proceed on understanding how inverse trigonometric functions work and how to evaluate them. These are the topics that we will cover in this lecture. We'll begin by understanding the inverse sine function and its uses. Next will be the inverse cosine function, followed by the inverse tangent function. Then we will go into the reciprocal functions, the inverse cotangent, cosecant, and secant functions. We have to know how to calculate inverse trigonometric functions using a calculator, and then we'll go into finding exact values of composite functions with inverse trigonometric functions. Now, before we go into the study of inverse trigonometric functions, let's talk about some key characteristics of the inverse functions in general. Now, the first thing to remember about any function is that the mapping between the y and the x values must always be 1 to 1, which means that every y value in the range of a function must map to a single unique x value. We cannot have the same y value emerging from two different x values. That's what we understand by a 1-to-1 mapping, and all functions must satisfy that property in order to be regarded as a function. And the way we determine whether a function has that 1-to-1 mapping is by performing the horizontal line test. What we do in the horizontal line test is, if we have a graph, we draw a series of horizontal lines through different points on the graph and check whether the line intersects the graph at only one point. If the horizontal line intersects the graph in more than one point at multiple points, then it violates the property of a function, which is that the mapping is not 1-to-1 between the y values and the x values. And when a function is 1-to-1, then we can assume that it has an inverse function. The other point about an inverse function is to review its notation. The way we represent an inverse function using this notation, f with a superscript of -1. Now, this -1 does not mean it's an exponent. It is just a notation to indicate that this is an inverse of a function. This -1 is just a superscript that we add to f. The other thing about an inverse function that we spoke about previously is that the range of the function becomes the domain of the inverse function. So, in other words, the y coordinate of a point of the original function becomes the x coordinate or the domain, the input value of the inverse function, whereas the domain value, the x coordinate, becomes the range of the inverse function. So the domain and the range values switch in the inverse functions. The x and y coordinates of a point are switched in the inverse function. And then here at the end, they say the graph of the inverse function is a reflection of the graph of f about the line y equals equals x. So it talks about the graph of the inverse function. Here I'm going to draw an xy coordinate plane and show the line which is y equals x. It's going to be the line that passes through the origin of the xy axis. And let's say we have a graph of the function which looks like this. Then the inverse function will be a graph which is a reflection of the original function across this line which is y equals x. So those are some of the important properties of any inverse functions that we must remember, which will also apply in the case of inverse trigonometric functions. We begin our study of inverse trigonometric functions with the sine function. We start by performing a horizontal line test to determine whether the sine function is indeed a one-to-one function or not, because only when a function is one-to-one, it will have an inverse function. In this picture here, this dashed red line has been drawn as the horizontal line passing through the sine curve, and we see that it intersects the curve at not just one point, but multiple points. Therefore, the sine curve, as shown here within the interval of -3 pi over 2 and +5 pi over 2, violates the property of a function being one-to-one. It will not have an inverse function if we consider the entire range of domain values of the sine curve. In order to find an inverse function, we have to restrict the domain of the sine curve where the horizontal line test will be successful, will pass the graph at a single point, and that's the interval of x values between -pi over 2 and +pi over 2. If we restrict the domain of the sine function between -pi over 2 to +pi over 2 and consider just this portion of the curve and perform the horizontal line test, we will see that it intersects the curve at only one point. Therefore, the entire sine function with all its domain values will not have an inverse function. We restrict the domain of the function and consider the interval of values only between x equals -pi over 2 and +pi over 2. The horizontal line test therefore shows that the sine function is not one-to-one. We have to restrict the domain of the sine function in order to get an inverse function, and that restricted domain is between -pi over 2 and +pi over 2. Here we have a formal definition of the inverse sine function. To summarize it, it says here, the inverse sine function is the inverse of the restricted sine function y equals sine of x within the interval of x values of -pi over 2 and +pi over 2 inclusive. Now here I would like to explain a very important concept of the relationship between the sine function, the original function, and the inverse function. Recall that we write the original function as sine of x equals y. Here the x values represent angle measures in degrees or in radians. Y represents ratios that come out after calculating the sine for a certain angle. So the input values to the original function are angle measures, whereas the output values are ratios. Now, when we consider the inverse function of sine, written as inverse sine of x, we still write the input variable as x equal to the output variable of y. But at this point in the inverse function, what we input into x are ratios. So what the inverse function is taking in are the ratios. In other words, the range of the original function becomes the domain values of the inverse function. We input ratios into the inverse function, and in exchange we get back angles for our output. So in the inverse function, the y values represent angle measures. All right. Now, because we have restricted the domain of the original function when coming up with the inverse function, the angle measures that we will get back from evaluating the inverse function would be angle measures only between negative pi over 2 and positive pi over 2 inclusive. All right, so you have to keep that in mind. The output values, the range of values from an inverse function would be angle values between negative pi over 2 and positive pi over 2. The input values or the domain values, which are ratios in the case of inverse sine function, would be any ratio value between negative 1 and positive 1. As far as graphing the inverse functions go, there are two possible ways of doing that. Let's study the first method. We already know that in an inverse function, the range of the original function becomes the domain of the inverse function, and the domain of the original function would become the range of the inverse function. Now, if we take different points from the graph of the sine function, switch the x and y coordinates and plot them on a coordinate plane built for the inverse function, connect those points, we will get the graph of the inverse function. Let's study the two graphs given here. On the left-hand side, we have the graph of the sine function drawn between a restricted domain of negative pi over 2 and positive pi over 2, because within that interval, the function will have a one-to-one mapping of its x and y coordinates. Now, the domain of the sine function are angle values. Therefore, we see negative pi over 2 and positive pi over 2 shown along the x-axis, and the output values, the range values, are ratios, and those are along the y-axis. What happens with the inverse function? The range and the domain values get switched. Therefore, on the graph on the right-hand side, we see the x-axis being scaled with the ratios between negative 1 and positive 1. That now becomes the domain, the input value of the inverse function, and the y-axis gets scaled with the angle measures. The angle measures that were the domain values for the sine function. In the inverse function, the domain of the sine function becomes the range of the inverse function. Now, to draw the graph, we take points on the sine function graph, switch or invert the x and y coordinates for each point, plot them on the xy coordinate plane for the inverse function, connect the points, we will come up with the graph of the inverse function. On the sine function graph here, for example, we see this point at the bottom has coordinates negative pi over 2 comma negative 1. On the graph for the inverse function, we see the point switched, correct? The x and y coordinates switched here. We see the x coordinate as negative 1 and the y coordinate as negative pi over 2. The same for the point on top. For the sine function, what was pi over 2 comma 1 has now become 1 comma pi over 2 on the inverse function graph. Therefore, the domain of the sine function now is negative pi over 2 comma pi over 2, which was always the case, right? The domain had the angle measures, and it's negative pi over 2 comma positive pi over 2 as far as the inverse function is concerned, and the range was negative 1 comma 1, whereas the domain and range for the inverse function goes like this. The domain would be all the ratios -1, 1, and the range would extend from -π/2, π/2. All right? Let's look at the second way of coming up with the graph of the inverse sine function, and that is to reflect the graph of the restricted sine function across the line y equals x. Now in this picture here, we see the graph of both the sine function as well as the inverse sine function. The red curve is that of the sine function and the blue curve is that of the inverse sine function. The dashed line passing through the origin is the line which is y equals x. So if we have the curve for the sine function between the restricted domain, of course, between -π/2 and +π/2, and reflect some of those points across the y equals x line passing through the origin and connect those points, we will end up with the graph of the inverse sine function. So that's the second method of drawing the graph of the inverse function. The next exercise is how to find the exact values of inverse sine function. In order to do that without a calculator, we will work with the special angles table, but only within the restricted interval of -π/2 and +π/2. And you have to remind yourself what we understand by inverse function. It tells us that give me the angle whose sine ratio is a certain value. So we can say, give me the angle measure whose sine ratio would be equal to perhaps -√2/2. And you would look up the table and see -π/4 has a ratio of -√2/2. Therefore, theta will be equal to -π/4. Again, theta is your output value. They've given us some steps to follow, but I think if you understand the concept and the meaning of the inverse function written out in this equation form, it should not be too difficult to find the value of theta. But let's go through the steps they've given us here. Number 1 says, let theta equals inverse sine of x. This is the equation. And then rewrite theta equals inverse sine of x as sine of theta equals x, but within this range of x values or this interval of x values. And then in step 3 it says use the exact values in the table to find the value of theta within this interval which satisfies sine of theta equals x. All right, but let's go through a concrete example and figure out how to use this process. Let's work through an example of finding the exact value of an inverse sine function. The question given to us is find the exact value of inverse sine of √3/2. Note that the input value to the inverse sine function is now a ratio. The output value is going to be an angle. We should read this expression as find the angle whose sine ratio is √3/2. Let's follow the step-by-step process as laid out here. Step 1 says write the expression in the form of an equation which is theta equals inverse sine of x. Of course, we have to plug in √3/2 into x and put it in an equation of the form which is theta equals inverse sine of √3 divided by 2. What this is saying again is find the angle measure whose sine ratio is positive √3/2. In the next step, it says rewrite this form of the equation that we wrote in step 1 as sine of theta equals x, but x has to be within this interval of angle measures from -π/2 to +π/2 because it's a restricted domain, correct? So we write it as sine of theta equals square root over 3 by 2. This is just writing out what we said before. What is the angle measure whose sine ratio is square root over 3 by 2. In the next step, we will pull up the table of special angles and look through the bottom row to find where square root over 3 by 2 is, and then search for its corresponding angle measure, the measure of theta. So we see in the row below, sine of theta, square root over 3 by 2 is right here, and its corresponding angle measure is pi over 3. Therefore, we can write the exact value of inverse sine of square root over 3 by 2 is pi over 3. Now in the next slide, they have worked out step 3 for us. I did everything over here. I gave the final answer as pi over 3. Let's go over to the next slide to see how they've worked out step 3. So here we are in step 3. It says use the exact value in the table to find the value of theta in the interval of negative pi over 2 and pi over 2. That satisfies the equation in the form sine of theta equals x. So they're asking us to do exactly what we did previously. We have to look for square root over 3 by 2. Let's do that. You see over here they box this column. Square root over 3 by 2 has an angle measure of pi over 3. Therefore, the angle in the interval between negative pi over 2 comma pi over 2, whose sine is square root over 3 by 2, is pi over 3. So the final answer is pi over 3 for this problem. Let's consider a second example where we have to find the exact value of the inverse sine of the ratio negative square root over 2 by 2. Right at the start, it's very important to remind ourselves that the input to an inverse function is a ratio, whereas the output value is the angle measure. In other words, we are looking for the value of an angle whose sine ratio will give us negative square root over 2 by 2. So in step 1, we first write this expression inverse sine as theta equals inverse sine of x. We write this expression in this form given here. Let theta equals inverse sine of x. And then we replace the x with the given ratio. That's what they do here. They rewrite it as theta equals inverse sine of negative square root over 2 by 2. They replace the x by the given ratio. And in step 2, we rewrite this equation and write it as sine of theta equals x. However, x has to be a value within that restricted domain within which we are working. Recall that we had to restrict the domain of the sine function in order to obtain an inverse function. And that restricted domain was within the interval of angle values from negative pi over 2 to positive pi over 2. Therefore, we rewrite it in this form, sine of theta equals negative square root over 2 by 2, which means that which angle has a sine ratio of negative square root over 2 by 2. Now in step 3, which will appear in the next slide, we will pull up our table of special angles and try to find the angle measure which has a ratio of negative minus square root over 2 by 2. Here we are in step 3. We have the table given to us, but the table has angle measures only from negative pi over 2 to positive pi over 2 because that is the domain that is being used in order to find the inverse function of sine. Use the exact value in the table to find the value of theta within this interval that satisfies sine of theta equals x. So x that was given to us was negative square root over 2 divided by 2. So we look at the ratios in the bottom row and look for negative square root over 2 by 2, which is this value here and then check the corresponding upper row value, theta, which is negative pi over 4. Therefore, the answer to this question, the inverse sine of negative square root over 2 by 2 will be negative pi over 4. And that's what they have here. It says the angle in the interval negative pi over 2 comma pi over 2 whose sine has a ratio of negative square root over 2 by 2 is negative pi over 4.